Welcome, ladies and gentlemen, to this RefComm 2021. I am Gopal Akilla, a SME for the Solvent Deasphalting Technology and working as Director in Wood. Wood offers licenses for UOP first-wheeler SDA technology, which has supercritical solvent recovery scheme. Today, I would like to talk about typical revamp objectives and bottlenecks seen in an existing conventional SDA unit. I shall also discuss the successful solutions that were implemented. Just a brief overview. Solvent deasphalting is predominantly used as a bottom-of-barrel upgrading solution. Simple solvent is mixed with vacuum residue feed, sometimes a blend of vacuum residue and atmospheric residue. Lighter and heavier phases separate. Solvent is recovered and reused. As you can see in the picture here, it's essentially a simple flow scheme. It's also elegant, purely a physical separation phenomenon, no chemical reactions, no catalyst required, no hydrogen consumed. Separation of products achieved by density difference between lighter and heavier phases, solvent selection and composition, separation conditions. Now, product yield and quality is dictated by the feed contaminants and their distribution. Maximum desirable SDA product yield is directly dependent on the solvent-specific insoluble content which drops out. Qualities of the product are targeted based on the downstream unit requirements. I request the audience to refer to my other presentation about solvent selection criteria in solvent deasphalting, which shall provide insights in tailoring a solvent deasphalting unit to the various downstream unit product quality targets. Typical SDA unit and its features. A brief overview of the older SDA units. First-wheeler SDA units with conventional solvent recovery were built from 1950s to early 1990s. Propane-butane solvents were predominantly used in these units. Solvent-to-oil ratio ranged from 5:1 to 8:1. Solvent recovery is through flash drums and evaporation. DO product disposition is lubes, hydrotreaters, and FCC. Asphalt product is sent to bitumen blending, fuel oil, and also as coker feeds. Currently, SDA units with supercritical solvent recovery schemes are offered for superior energy savings. Audience shall note that UOP first-wheeler offers supercritical solvent recovery units as they are energy efficient than the conventional units. Now we'll talk about the existing unit. This is a case study. You can see there are two RDC columns used in this unit. I'm showing a PFD for that, where these two RDC columns have steam coils on their top. The bulk of the DO solvent leaves the top of the column. Asphalt solvent mix drops from the bottom. Now we'll talk about a separate section, which is high pressure and low pressure preheating and solvent recovery sections. So you can see some layout is shown. The colored section is the HP section, and the remainder is the LP section. The RDC column's overhead is preheated and sent to HP flash tower, which is on the top of the sketch. The solvent vapors from this tower exchange heat with the bottom liquid of the same vessel, condense, and then get collected in the HP solvent drum shown at the bottom. A HP solvent pump pumps this solvent and sends it to the extractor column. The HP flashed or bottom liquid gets preheated in the thermosiphon reboiler shown on the top right of the sketch, and then this DO solvent mix is fed to a DO stripper. The DO stripper overheads and the asphalt stripper overheads. They get combined and get condensed in this LP condenser section shown, get collected in the LP solvent drum, and then the recovered solvent is sent back to the extractor. Now what about the RDC column bottom stream, which is asphalt solvent mix? The asphalt solvent mix is preheated in a asphalt fired heater, then sent to the asphalt stripper. As I explained earlier, the stripper overheads, which is predominantly solvent, is collected, condensed, and recovered in the LP solvent drum and sent back to the extractor. The bottom of the asphalt stripper is the asphalt product, which is sent to storage or blending. Now, SDA unit revamp objectives and bottlenecks. As I explained, this is a case study. The new capacity desired is 15,000 barrels per day from 11,000 barrels per day. Mixed butanes as solvent with 6:1 solvent to ratio to improve DO product quality with changing feedstock. Review the possibility of converting to a supercritical solvent recovery. Identify and address thermal and hydraulic bottlenecks. Eliminate foaming in HP solvent flash tower. Minimize emissions from the SDA unit and its product storage. So these were the main objectives, which is essentially typical in most of the units. Forstwiller conducted studies, and then it has identified two cases: conversion to supercritical unit, which is a case by itself, and the second one is revamping the existing unit as is with minor modifications. The common objectives for the both cases are hydraulic limitations for the higher capacity, thermal limits for heat transfer, falling issues causing significant downtime, long history of foaming causing overflow in the critical vessel leading to solvent contamination, pump damage. So I showed a couple of figures. We will be talking in detail. So these were the bottlenecks that were identified. Now we shall discuss the modifications. The first case, which is essentially conversion to a supercritical solvent recovery mode. Conversion to a supercritical unit has energy savings. A new DO separator and 3 exchange services are required. Conversion to supercritical unit will eliminate the need for many of the existing equipment with the recovery of the plot area. You can see this simplification of the flow scheme as shown in the figure. Earlier I have shown the layout of the high pressure, low pressure section. The colored area, which is the high pressure section, will essentially get eliminated by adding this exchanger. What exactly I mean? So if you see here in this picture, the RDC column, the internals will be modified, that is one, and the LP section, which has pitch stripper and DO stripper, essentially remain the same. The internals might be replaced. These three new exchanges need to be added along with the DO separator. This is the supercritical solvent recovery. This is what will happen if you want to convert. So now this scheme is energy efficient. We can achieve twice the capacity, replaces the flash drums and evaporator systems with this energy recovery mode, and it's a high quality DO product. Now, as the capacity is increased only 34% and not 100% with conversion, the client opted to debottleneck existing unit instead of conversion to supercritical unit to reuse most of the equipment. You may want to know how DO quality improves. DO quality improvements such as metals and CCR can be seen with higher solvent to oil ratio in a supercritical unit with no issue of energy penalties associated with high SOR when compared to conventional unit described earlier. I covered this effect of solvent to oil ratio in my other presentation. I request audience to refer to it for details. Extraction limits. Each RDC extractor capacity need to increase by 34%. Steam utility shall also increase. Now what is the solution? Installed modern Soldier proprietary packed beds in one of the RDC columns for the full revamp capacity. Eliminate the second RDC column. No steam required. So these were the benefits of changing the internals in one of the RDC columns to packed beds. You can see two packed beds shown in this figure. What they do? They promote even flow and velocities, encourages contacting, encourages agglomeration of pitch droplets. You can see in the picture. Provides additional settling contacting zones, reduces the extractor vessel size, highest solvent quality at the final DO extraction, DO product quality improvements by lowering pitch entrainment, which is an important criteria for FCC and hydrotreaters when the DO is used as its feed. Now, we'll talk about the hydraulic limits. Higher solvent to flow to recovery section causes earlier the design was 5:1, now we increased to 6:1. Higher preheat required for solvent recovery. So the RDC column overheads will flow through this preheat exchanger to the HP flash drum on the right hand side. Inadequate surface area in this preheat exchanger and the heat recovery exchanger. These are the two exchangers shown are limited. Solution: installed new hot utility exchanger in parallel to the existing to improve preheat for the higher flow. Installed additional recovery exchanger to minimize hot utility. So you can see a parallel exchanger is shown on the preheat side as well as on the recovery side. Solvent emission through DO product. What are the causes? Thermosiphon reboiler in the LP flash tower is falling often, causing unreliable preheating before sent to the DO solvent stripper. So the LP flash tower, which is bottom of the high pressure flash tower, this thermosiphon reboiler is found to be falling so often the downtime is significant. And because of the unreliable operation, DEVA product stripping temperature is also low, where the enough solvent is not separated from the DEVA product. Now, what is the solution? A, a forced circulation reboiler is added in place of a thermosiphon reboiler, where you can see a pump is added at the bottom, and this has essentially eliminated the downtime and provided consistent stripping temperatures to recover solvent from the DO. This modification helped in reducing the concentration of the solvent in the DO product to a minimum in a ppm, almost like a ppm level, thereby eliminating emissions from the DO storage area. Now, foaming in the HP flash tower. Long history of foaming, mainly due to the nature of the feed. You can see on the top of this figure, the top vessel is the HP flash tower. The circled area is where the foaming is happening. Anti-foam had a minimum impact in reducing foaming. Tower level could not be measured. Solvent in the tower is at saturated conditions. So any pressure fluctuation will flash off this solvent in this tower. DO entrainment along with the solvent is causing HP solvent pump leakage and damage. So the HP solvent pump is located in the bottom of the HP solvent drum. So that pump damage is recurring. Now what is the solution? Increase the preheat temperature by a few degrees in the new preheat exchanger, which is added to the parallel to the existing. Install the vortex tube clusters in the HP flash tower. You can see the picture of the HP flash tower with the vortex tube clusters. These vortex tube clusters are maintained with a liquid seal at the bottom. And improved pressure control to minimize flashing of this liquid in the bottom seal. Retuning the control valves is critical for this stability in controlling this tower. So how these VTC tubes work? The two-phase saturated feed is distributed evenly with a new feed distributed into this vessel. Vortex tube clusters worked very well in this low surface tension application, separating solvent vapors and concentrating DO in the bottom liquid seal. These devices have eliminated the long history of foaming to the satisfaction of the client's operating team. Many maintenance issues related to entrainment and HP solvent pump damage were essentially removed. Now, higher solvent flow to the product strippers. Hydraulic capacity is limited. Inadequate stripping for the revamp capacity. Solution: installed a new baffle trays in both the DO strippers to handle the higher capacity. SDA unit startup. Unit was started successfully. A test run was conducted for full evaluation. All equipment modification found to be performing well at a full revamp capacity. Product rates and qualities were superior to those of the guaranteed values. Summary: older SDA units can be revamped easily for higher capacity using existing equipment. No major vessels are required to double the capacity. Modifications are minimum with internal replacements and mostly based on hydraulic and thermal limitations of the existing equipment. Conversion to supercritical solvent recovery will improve energy savings up to 55%. This requires new DO separator and 3 new exchangers. Supercritical units have simplified flow scheme, energy efficient, and are also low capital intensive. One can recover the investment within 5 years. They can be integrated to a coker or hydrocracker or waste breaker to offer highest economic returns in investment. So again, I'm showing a supercritical unit, which is a simplified scheme and a layout of the same unit in the bottom. Thank you all for giving me this opportunity to present this topic. I shall open the floor for any questions. Thank you.